Hello, my name is Mohammad Irfan Khan and I'll be presenting Bayesian Similarity-weighted Aggregation for Federated Brain Tumor Segmentation. So the overall objective is to develop a Bayesian generative formulation for federated brain tumor segmentation. Uh, so overall, before diving in, I need to give you a bird's eye view of the federated dining. So the idea is that sensitive medical data is difficult to share. There are bureaucratic challenges and there are regulations which make it difficult to pool all of the data at one central location. So the idea is rather than bringing all the data from all the different silos to one central location, ship a machine learning model to these individual data silos, which are called collaborators, and then do the training locally, and then only send the trained parameters to a central server where they are aggregated intelligently and then shipped back to each of these individual sites called as collaborators. So by this, even if one of the sites has lesser data volume, they can benefit from the other site without actually having access to the data. So this could be these different collaborators could be hospitals, research centers, clinics, and overall this is privacy compliant and it suits this uh, medical data problem where it supports model development without data sharing, and even ideal for geographically distinct and distributed data sets. And there are certain challenges in brain tumor segmentation, for example, data sensitivity, which I mentioned. It is there are strict regulations like GDPR in Europe and HIPAA in US, and the data can be variable across institutions, and there are computational constraints as well for local training. This is why this problem was really important, and I worked on this one. Overall, regarding the data set, I had 1251 MRI scans, which are publicly available, and 219 validation data set. I had two different partitions for showing the data distribution of the patients. This is a non-IID data setting. The overall uh, uh, if we see the data set, for each of the patients we have four different modalities: T1 FLAIR, T2, T1 GD, which is shown on the right side of the of the slide. The left side is the segmented part, which is the ground truth. Overall, there are limitations to the classical methods like Federated, which is not suitable for non-IID, and there are other approaches which require user-defined parameters which need tuning, and they are not inherently generalizable to new data sets. So this is why we introduced similarity-weighted aggregation, which with which we participated in the FETS challenge. It's a global AI challenge, the first one for federated dining. So this method was created, which is suitable for both IID and non-IID dataset. Uh, Overall, rather than simple averaging, it does the weighted averaging, it ensures that the mass model captures the consensus of the most of the collaborators, and I'll show all the different steps in one of the slides. I added the Bayesian part into it because there are certain challenges as well. For example, you have high dimensionality problem, small and large p, where you have less number of cases, high number of features, and there can be analytical challenges. For example, as the number of features grows, finding closed form solutions become increasingly difficult due to analytical intractability. And there can be non-linear relationships among the features, which can be complex, and so this makes the traditional analytical approaches difficult to capture to explicate the latent structure within the data. So this is why, because of non-linearity and high dimensionality, we require numerical approximations or simulations for analysis or modeling. So the overall target is to model uncertainty under limited data settings and incorporate prior expert knowledge into it. Overall, the assumption is that the observed data is generated by an underlying latent process, and hence we use the Bayesian methodology. So how does SimAgg work, and where the Bayesian part comes in? Overall, if we have like 20% of the overall collaborators participating in one federation round, what we do is we take an average of these collaborators parameters, and we compute a similarity score, which is like how the distance between each of the collaborator and the overall average. And we have two weighting factors, UC and VC. So first we calculate the similarity scores for each of the collaborator with the average of the parameters of the collaborators participating in that federation round. The second weighting factor depends on the data volume, and PM is the PM was the parameter which is dispatched for the next federation rounds. Now, overall, we process 318 tensors in each federation round by the aggregator method. 118 of them are directly related to weight or bias. 4 out of them are related to output layers. So what we are actually doing is we are putting some priors on these output layers, where which is shown in the plate diagram. For example, the outer layer represents the number of collaborators, I from 1 to n, and the inner layer is the parameter layer, which is from j, and this is influenced by bc, and we are calculating pij. So we give PM and BC to PIJ, and we are also putting hyperpriors on BC and PIJ. So after we calculate Pij, that is the one which we dispatch to all of the other collaborators. And this is the stand code which we have used for the overall segmentation. We have used 3D unit, which has 95 days, 33 million parameters, and it's a 3D unit architecture optimized for segmentation tasks. We have two performance matrices. One is dice score, one is house top distance, and for implementation I've used OpenFL platform and used STAN and RWAYS. STAN for statistical computation, RWAYS for visualizations. Overall, these are the results. We have the performance metrics. I've simulated time, segmentation accuracy, energy consumption, the dice scores. Overall, if we compare Bayesian SimAgg with SimAgg, overall it takes almost 60% of the time to get to almost similar convergence scores. So overall, it achieves convergence faster, and achieves higher segmentation accuracy for tumor subregions. We have 3 tumor subregions. We are segmenting 3 tumor regions: whole tumor, tumor core, and enhancing tumor. And it is also efficient for handling non-IID data under uncertainty reasons. So by leveraging the conclusion is that by leveraging probabilistic modeling and effective collaborator selection, Bayesian SimAgg enhances model accuracy and robustness. Our future direction is that we want to use, instead of using STAN, have a pre-trained neural network for faster posterior estimation, which is called as amortized inference. And I want to explore Riemannian geometry for advanced parameter analysis, which would be geometry-based models, and also to explore the impact of vague priors in federated learning setups. Overall, I want to acknowledge CSC for giving us the resources, and Business Finland for giving us the grant to work. Thank you.